let me start kind of by trying to get some order in this chaos. So there were some mistakes made obviously on the web. MAE 165 and MAE 265 are one and the same class, they are together. Now MAE 165 knew there was a class every Monday, which is kind of a class, a discussion class, which is only 50 minutes. Now the graduates did not know that. Am I right? Is that all your understanding? I want to see a lot of nods.
Yes.
Yes, yes, yes. Okay. Because if I don't get nods, I say, damn, I still have it wrong. But so you all understand that. Now, there might be some of you that have a problem because you didn't plan for that 1 hour. Many people have written me emails. I didn't know about that, so I cannot come today. That's why probably we will not get our full 54 or 58 students. Huh? But in any event, this class will get a bigger, more comfortable class to work in together. We need these extra Mondays. They will often not be discussion, but there will be preparation for a practicum. Because this being about advanced manufacturing, we want to give you hands-on. We want you to do things, to make things, right? Because it's about bringing advanced manufacturing back to the US. And this is why this class has blessing from the Dean all the way to the Vice Chancellor. And we actually want to make it next year an engineering class, not MAE, but engineering 265, 165, so we can get everyone, bioengineering, chemical engineering, anyone who thinks that manufacturing is important to this country and maybe to your career. Right? So that's kind of the background. So forgive me if I will have to repeat that tomorrow. Huh? I will try to say it slightly different so you don't get too bored. Okay. So I will try to go over the topics we want to cover. So this is my name. Some people pronounce it Madou. It's Madou. Can you do that? Madou. Pretty good. And Swati Sharma will be a TA. This is also new. Normally in a class like this we don't get a TA, but because the Dean is so interested in this happening, we even got a TA. She will mostly help you when we have the practica, the scheduling. Why don't I go to that first actually to tell you what the practica will involve. So in terms of practica, so you guys will tell them what I already said, right? But probably I will repeat most of it tomorrow anyways. So the practica will be this. You will be introduced to CNC machining. Who knows what CNC machining is? 1, 2, raise your hand. You don't have to be embarrassed if you don't know it. So what does it stand for? Computer, C, N, numerical, and C, control. Good. So you will be actually going to a workshop and show how you go from a design to actually machine something. Number 2, you will do soft lithography. Who knows what soft lithography is? Maybe 2 or 3 of you guys, right? But don't worry, right? That's the idea of this class. You're going to learn practically what soft lithography is and do it in the lab. We're going to have, this is kind of easy, you're going to have a clean room visit. So for those people that hear about dry etching, plasma, CVD, metal deposition station, at least you see it. You see the machine where these things happen. So that's number 3. 4th, you will do rapid prototyping. So what is that? You're going to do one of these 3D printing things. You all heard about that. That's become very popular in the news. In the building across here, at the 4th floor, we have an organization called Rapid Tech. And they will guide you all the way from the design to a Bluetooth device. So you're going to design it, and then you're going to make it. You're going to print it. So I'm going to give you a bad story of something that happened with this in previous years. We might have to turn off the video because it's kind of bad. But so you know how these things are supposed to look, right? They fit in your ear, right? And they have like this little loop. So some of the people had designed it so that the thing came on this side. So you would put it on, and instead of going in your ear, it pointed outwards. Design error. But you also have to have the size in mind. And someone had the size wrong by a factor of 10. And you know what it looked like. Man, it was so embarrassing. So I had all of these printed prototypes, and I had to give them back to the students, right? And everyone was kind of laughing. By the way, it was purple. And I knew just by looking who had made that device, and that girl didn't want to come forward, right? So that one thing remained there, so I still have it. Anyway, so make sure that you also take the size of things in mind. Anyway, so we're going to do rapid prototyping, and then finally, in my own group, we use compact disc CDs to do microfluidics. And you're going to be learning on how to make a CD, not to put music on it or videos, but actually to do a diagnostic test with it. So these are the practica you will have. You're a big group, so there will be some challenges in organizing this. So I hope you guys are patient with us. It's the first year we are doing this. So do tell me what's going well, what's going wrong as we go along. So one of these things is the temperature is too high. We have too many people in the class. I already told you we hope to take care of that by Monday. Okay. So what topics are we trying to cover instead of going through this boring list? And this will all be on the web, by the way. So probably by Wednesday or Thursday, if you visit the BioMEMS Net website, you will find all of the class notes, print those out and put them in a folder. And so you will find the syllabus there. But I rather have the syllabus incorporated in my class 1 material, which I will start now. I just told you so far about the practica you will do. How many are we now?
42.
42, okay. So. Suppose it failed. Suppose we turn off the light a little bit. Can you control it from there, that side?
I think you got it on your...
Is it here?
Yeah.
I think you're right, yeah. Usually people don't all show up, and now they do. Damn. What's wrong with you guys? So, who knows what manufacturing is? We're going to start with that, like with some definitions, and so could I have someone volunteering to do that while I'm trying to call up this class?
Isn't manufacturing just the process of making something?
Yeah, right, that's simple. Yeah. Instead of talking about it, and instead of this big digital revolution we have had, right? We have come in an age where everyone thought things can all be done virtually, isn't it? Mechanical engineering got less and less students. They went all to electrical engineering or bioengineering because they thought, you know, making things is dirty, isn't it? There's a little bit that attitude, especially in the United States. That attitude, by the way, you will not find in Germany, Japan, and Korea. And now China, countries that are doing very well. And it might have something to do with the fact that they recognize to create a country wealthy and maintain the wealth in a country, you can do a couple of things. 3 things. Let's try to find out. What are the 3 things we can do? You can mine things. Yeah? You mine it out of the ground. Petroleum, metals, you sell them. You can make things. Right? What's the 3rd thing?
Awesome.
Sorry?
Sell things?
I'd like you guys to find out what the 3rd thing is. It's going to be your homework. 3 things that really make the wealth of a country.
Innovate.
Yeah, but that's manufacturing, right? Making things. So we got it in these categories.
Innovate.
Innovate, maybe that's part of manufacturing, right?
Invade.
Sorry?
Invade. We invade other countries.
Oh, do we do that? I hope we don't do that anymore. You're not serious, are you? Are you?
Well, that's how Rome gets so big.
Yeah, but look what happened. You don't want to be there, do you? Even now, look, Italy, what happened with it? Britain, what happened with it? It's a good discussion, though. I agree. It's kind of all part of the same thing. I'm not finding this yet. We can still talk about this concept. Why is manufacturing becoming so important? So I'm going to ask this question again. Obama administration, what have they started doing? Have you followed the news a little bit?
Outsourcing.
Yeah, but they want to stop outsourcing. They want to bring some of the manufacturing back. So there's these huge initiatives where they have announced we're going to create institutes in the United States that allow the US to not only invent, but also make the things they invent. In other words, they want to make the loop between design and making a product shorter, so you have more chance that the investment of the government, be it NSF, NASA, NIH, that you can actually profit from it. My own field is MEMS and nanotechnology. And what we have witnessed that actually most of the money made on these things, on micromachining and nanotechnology, is made in Bosch in Germany, Olympus in Japan, in Korea, and now more and more in China. And it has a lot to do with the fact that this country has lost the nerve, so to speak, of actually making things and has considered manufacturing more and more of a dirty word. And now it's odd because if you go in a manufacturing plant today, it doesn't look like a manufacturing plant of 50 years ago. It's actually very clean. It almost looks like a clean room. And you need more and more educated people, very high level, that know how to design and put that design into a manufactured good. So we need to bring up the level of our students dramatically, even to get into manufacturing. Because you know that some of the companies from abroad that come to the US, they can actually not staff the companies because they don't find people that are competent enough to actually do the technician jobs. That's a very sorry state of affairs. So in a way, I'm trying to make you guys a little bit more realistic. We have bet too much on everything is going to be digital, virtual. That's not true anymore. Because nowadays, there's a lot of countries that are as rich as us, maybe richer, and anything we invent, they can implement faster than us. So all we can do is get back to education, to bring our students in the US up to the top level as high as we can bring them. So now I'm going to try to see if I can get my class. I couldn't find it yet. Any questions on what I just said? It sounded like philosophy, isn't it? It's a little bit philosophy. By the way, you people that came in later, don't worry, we're looking for a much bigger class. I see you looking kind of like, what is this? So you can sit here, you're okay. Please come sit here. You're so uncomfortable right there with the camera, so. Oh, now I embarrassed you, did I? Sorry. Any question?
What's the third one?
Yeah, that's up to you guys. You're going to tell me 3 things that make a nation rich and wealthy and hopefully sustainable. What are the 2 so far? No, come on, I know. You're a good student, you know.
Manufacturing.
We mine something, we make something, and the 3rd one, by the end of the class, we will have it.
That would be another M.
M, you think it's all mining, manufacturing? Oh damn, I'm thinking about a bad one. Anyways. Anyways, so advanced manufacturing, you can organize manufacturing in many, many different ways. And one way how you can organize them is by the way the energy you apply to a material is categorized. You know, there's various forms of energy that you can consider. It could be mechanical energy, so you drill something or you carve something, that would be mechanical. It could be electrical energy. It could be heat energy, such as with laser cutting. It could be chemical energy. You will see that manufacturing processes that are out there, we can probably organize in 7, 8 different ways. This is one where we do it in terms of the energy you use to make something. So mechanical, electrical, heat energy, or chemical. Now we will find in the course of this class, this is not always very easy. to apply rigorously this kind of classification, because sometimes a process will have something chemical but also something electrochemical, or it will have some mechanical together with some chemical, etc. So it turns out that in most of the cases it's not just one of those four, it's a mixture. And especially if you want to categorize processes between subtractive and additive, we will find that in the case of subtractive techniques we can apply these four methods, but when it's additive we cannot. Okay, I already overwhelmed you with new words, right? One way of categorizing manufacturing is in these four terms, the energy involved. Another one is, you just saw it, additive versus subtractive. Now that's kind of easy, right? What will it mean? Additive manufacturing means you have a workpiece and you keep on adding material to make something. That's additive. What's subtractive then? You take parts away, right? And so we will see that in the case of subtractive techniques, applying on top of saying it's subtractive, that it happens mechanically is rather easy. But if you try to do the same in the case of additive manufacturing, you'll get in trouble quite a few times. Okay, first exercise. What you're seeing here is a human hair. So what is the thickness of a human hair? Diameter?
Really small.
Very small. Today is, by the way, vectoring your intuition a little bit in sizes. How big are things? Right? A human hair,
1 to 10 micron? 40 micrometers.
you're getting closer. Between 80 and 100 microns. I forgot, red hair is thinner. It doesn't mean you have less of it, but it means it's thinner. And I think blonde is next and black is the thickest. I think it goes up to 100 microns. So 100 micron. By the way, write that number down. 100 micron, for some reason, in manufacturing is like a critical cutoff to switch from one manufacturing technique to another one. 100 microns. So this means this thing is 100 microns, and some guy, for some reason, cut holes into that hair. How did he do that? So I hope by the end of the class you will figure out, maybe even now some of you guys have an idea how this person managed to cut square little holes in a hair. Oh, by the way, is it an additive technique or a subtractive technique? Yeah, good. We got that right, huh? But now, which one of those did we apply? Did we use your father's drill? How big is the smallest drill you think people use mechanically, typically?
130 seconds a million.
Actually, it's the same number I mentioned a bit earlier. It's that 100 microns. That's kind of the smallest drill bit you will have. And we will see, if you want to machine something below 100 microns, you're going to go from mechanical machining to lithography. You cannot do it anymore with mechanical means. So one of the classes will be lithography. How comes you can make these small things if you use lithography instead of mechanical machining? Huh? So anyone has a better idea? We have two questions already for you guys, right? The first question was that third way you make countries rich. You were going to do it by invading. Maybe you will say what country to invade. Huh? And the second question is, how do you think this actually was done? I know this is very early, right? We are still talking about the syllabus, but come on, we can get you thinking, right? Anyone has an idea by now? What could be used? We know already not the drill, right? Not the drill. Drill is much bigger than the human hair. And probably the hair will also go around the drill, no? Anyway, so things that we want to achieve in this class is this. So students, guided by specification and a design, will be able to decide. So you will have a design to make something. And you will be able to decide when to apply mechanical machining versus lithography-based machining. You actually already have a clue now on this first one, right? What would be a clue? The 100 microns, eh? Good. 2, what type, suppose you decide it needs to be mechanical, what type of mechanical machining to use, and what type of lithography to use. Number 2. 3, when to employ bottom-up versus top-down manufacturing. Again, new words. We have introduced already 2 ways to classify manufacturing. The first one was by energies, right? Second? Yeah. Third one, bottom-up versus top-down. Now, what is that? Bottom-up versus top-down. This is a really interesting one. You see, everything around us, including ourselves, we are made top-down or bottom-up? Bottom-up. Nature works bottom-up. You know, it built things by starting from amino acids, goes to proteins, goes to bigger and bigger structures. We don't build things that way. We take a chunk of silicon, carve it, make it smaller and smaller, make a nice C. Just the opposite. Interesting, right? So human manufacturing, till about 20 years ago, was all top-down. Nature always has been bottom-up. Now you guys are living in a very interesting era, because many objects now we can make either way. We can make them top-down or bottom-up. And so there's more and more overlap between these two techniques. So in this class we will learn about some ways that you will call bottom-up, other ones top-down. So there you go, we have already 3 ways of manufacturing classifications. 4, when to choose serial, batch or continuous manufacturing. Okay, yet another way of categorizing manufacturing. What are the words we have here? Serial, batch or continuous. The words are kind of self-explanatory. Serial will be, okay, I'm making skis to go skiing. You'll make one at a time, right? What is batch? Batch, for example, is the silicon process. In integrated circuitry, on one silicon wafer, we have 600 chips. That's a batch. Continuous is newspaper printing. Where is the world leading to? It's moving from batch to continuous. For example, if I want to make glucose sensors for any patient, or I want to make sensors that are embedded in your cloths, I need to make them very inexpensive. I cannot make them with batch. I need to make them continuous. Right? So that's the 4th method, actually. And then 5th, you will learn what kind of rapid prototyping method to select. And that will be these classes that we give in respect to 3D printing, and actually you will get to do it yourself. Right? But you will figure out there's at least 7 different methods of rapid prototyping. Which one should I use if I have that design and that product I'm trying to make? We will give you a logical decision tree. So if it's like this, let's say it's much smaller than 100 microns, yes or no, I do mechanical or lithography, right? So we'll make a decision tree that helps you through all of this. And so examples will include products going all the way from nanometers to centimeters. So this is very ambitious class. So I talked a moment ago about size of things. We'll talk about making products ranging in size from nanometers to centimeters. So I'm giving you this little video to kind of just broaden your mind, to think about nanotechnology, MEMS and manufacturing all in the same vein. Manufacturing and nanotechnology, you know, is actually the same thing. If I cannot manufacture nano products, I'm not a nanotechnologist. I want you to feel proud that you're interested in manufacturing. This video kind of gives you an idea of, we call the scale of things. To start having these ideas, when I asked you what's the size of a human hair, you immediately have a number. The size of a cell in your body, size?
A couple microns?
Yeah. 5, 6 microns, right? So let's see if I can figure out the lights here. I also would need a sound. Maybe this can be, you guys are going to be very quiet, right? So maybe if I put this very loud, you will hear it. And this lady pronounces things very well. She has no accent like mine. Who knows where my accent is from? Too many people know that now. Usually no one knows. Something is wrong. How come so many people know? Yeah.
You like Belgian bear?
That's absolutely true. Who told you that? What are some good Belgian beers?
Stella?
No, it's not a. You know, this is all Budweiser. This is not a good beer.
In the past, there were scientists who studied the stars,
Do you hear
and
it?
scientists that studied atoms. And even today there are scientists called
Is there a
cosmologists
switch there?
and scientists called particle physicists. Yet there is a direct connection between the physics of the very large and the physics of the very small. Because even the largest objects in the universe are made of exactly
Can
the
you
same
hear it?
building blocks as the smallest things. Measuring things is at the heart
Oh,
of
you can't see anything.
one of science's great achievements is to have
Just give me a second here. I tried to. We're going to do this right.
to the size of the tiny particles that make up the heart of an atom.
So don't worry, I'm going to replay it till I need to find how to do this here. Do you see anything at all? Nah. Maybe Liverpool, 14 kilometers across. Okay, I'm going to try to interpret. Street in Liverpool, size 1/4 of a kilometer long. A house, 10 meters. Easy, right? The kid, 1 meter. The eye, 15 centimeters. Pupil. Yeah, 1 centimeter, good. Now we're gonna go in the eye. Cells. Approximately in meters, 5 microns, 10 to the minus 6, 5, 10 to the minus 6. DNA, 10 to the minus 9. And by the way, we can build with DNA. We can make things with DNA. DNA is making things, you know that, through protein expression. Hydrogen, what was it? Hello? Okay, what was the smallest thing? Hydrogen, then the nucleus, nucleons, size. Should I redo it? You don't need to remember it, but you need to have so far one number in mind. Only one so far. No, 2. 100 microns, right? And 5 to 6 microns for a biological cell. Let's keep those in mind, kind of as our anchors. He's talking about a much more things. He's talking about how scientists are now getting more and more better at understanding huge things. But when they understand huge things, they also start understanding better very, very small things. What we talk about is making these things from the small to the large, how you make them. We will find that technology often is actually driven by what we will talk about in this class. I'll give you an example. You know when nanotechnology really took off? That is when we built an instrument called an atomic force microscope. An atomic force microscope is able to build atom by atom, bottom up, things that are bigger and bigger. That was the start of nanotechnology. A machine, something that could make things, could manufacture things. Write that down, AFM. We're going to have a class about that. Atomic force microscopy. Syllabus topics. So finally get to the syllabus, but it's better than going through this dry syllabus you'll find on the web and make it part of my class. We'll talk about in the first class, hopefully today, the difference between sealed batch and continuous manufacturing processes. That will be easy. I already gave you examples, right? The second one will be a little bit more complicated. I want you to understand the difference between relative tolerance versus absolute tolerance in machining. Then we'll talk about principles of manufacturing processes, mechanical energy dominated, cutting, shaping, forging, ultrasonic machine. By the way, the only thing we're going to cover today is 1 and 2. And as I told you, because this class is kind of in chaos, I might have to repeat some of that tomorrow, right? But I still want you to come, okay? But then in later classes, so we will talk about those processes, Roman number 1 that are mechanical. Then we'll talk about Roman number 2, electrical, energy based. What were the 4 ones? Mechanical, chemical, heat, and electrical, right? And so we'll go over examples in each of those. By the way, this little car you see here, you'll see it better when you print it out. It's sitting on a dime, and it's a car that actually runs, and it's been micro-machined with a set of technologies we will specify. And so here is 4, chemical energy. Then we will talk about next generation lithography tools. We talk about nanomachining tools, top-down versus bottom-up. You already know a bit about that. Rapid prototyping, also called layered manufacturing. And then this is this decision tree, matching manufacturing process to product specification and design, leading to the manufacturing process decision tree. So are you ready for that? That's what we're going to do this quarter. Definition. So class 1 now, we are on to class 1. So I gave you the syllabus, I gave you a bunch of philosophy, and I also told you it's way too hot here, that I like Belgian beer, and what else? I told you about the 100 microns, the 5 microns, and 2 homework questions. 2 homework questions so far.
The third thing?
The third thing, right, good, and the hole in the hair. How do you drill that hole in those hairs? So probably tomorrow I will just single one of you guys out and say, you know it now, or you figured it out. But all we will do today is definition of manufacturing. And as someone said, it's kind of like, isn't that like too simple-minded? It's just making things, right? So then we'll give you some examples of serial, batch, and continuous manufacturing processes, and end up with talking about the difference between relative tolerance versus absolute tolerance. I hate these slides with just a bunch of words. So someone is going to read it. Someone with a good, strong voice. Mitch, read this for us loud. I don't want to do it. It's too hot.
Manufacturing is the use of machines.
Come on, stand up. Loud. He can.
Manufacturing is the use of machines, tools, and labor to make things for use or sale. The term may refer to a range of human activity from handicraft to high.
Give it some.
But
Good.
is most commonly applied to industrial production, in which raw materials are transformed into finished goods on a large scale. Such finished goods may be used for manufacturing other more complex products, such as household appliances or automobiles, or sold to wholesalers, who in turn sell them to retailers, who then sell them to end users, to consumers.
Credit to Wikipedia. Okay. So, but yeah, it's about manufacturing, it's making things, and it's one of the 3 things that makes a country wealthy. So, serial, batch, and continuous manufacturing processes. Things used to be very expensive, even in the electronics area. You know, instead of transistors, we had something called lamps, bulbs, and they were made one at a time. Perhaps they costed $20, $30. Now we make silicon chips. I wonder if you guys know that. A MEMS silicon chip, an accelerometer, the one that goes in your car for the airbag release. You know how much that can cost nowadays? 100?
Couple cents.
50 cents. Isn't that amazing? And the complexity in there is fantastic. It's amazing. Why has that been possible? Because we are not making them in a serial fashion. We don't make one at a time. We make maybe 2,000 all at the same time on a wafer in the silicon process. Starting with lithography, on one silicon wafer, you might produce sometimes 6,000, 7,000 devices. That can mean that you could have the whole supply of the United States of a certain object made in one day. So you can imagine what happened to the whole society when we moved from serial to batch. Now the next thing, and more people are looking at that, to actually make clean rooms continuous. So instead of one silicon wafer, just like a newspaper, you have a band of material you process. And that would be continuous. Huh? So single unit production or serial production. Next is batch. And the primary characteristic of that is that a group of identical components are completed at a workstation before they move to the next one. IC fabrication is the best example of that. In other words, that same PVD, physical vapor deposition, or CVD, does not happen on one device. It happens at 1,000 devices all at the same time. And you then also have a good chance that these devices are all quite similar, right? So you make them more reproducible. And then continuous production is a method used to manufacture, produce, or process materials without interruption. So you do it with a roll that supplies a material, a substrate, to another roll, and in going from roll 1 to roll 2, they call this all the way, also by the way, roll-to-roll processing or continuous manufacturing, you continuously make a product. It's just like you're printing a newspaper. So examples follow. So making a pair of skis, one at a time, expensive. It would be hard to miniaturize those, huh? Right? Anyways. Batch production, so IC fabrication, and then this could be a continuous process where, in this case, wood is being laminated, and so you literally make kilometers of the good continuously. So these are examples of each of these. By the way, how many methods we already have identified so far to categorize manufacturing? Can you name them? So one was in terms of the energy use, right? And we have these 4 different energy fields. Then additive, subtractive. Then top down, bottom up. Then sealed, batch, continuous, right? These all kind of, and you will even see more methods on how to. So you might then say, if I say laser machining, you might start thinking, okay, laser machining. How will laser machining work? You will have a laser, one hot spot there on your workpiece. So will that be serial? Will it be continuous? Is it batch, etc.? I could ask you, categorize laser machining according to these topics. What kind of energy is it? Right? Is it serial or continuous? Is it additive or subtractive? Is it top-down or bottom-up? So each of these methods you will be able to categorize according to these categories. What should I call them? Methods to categorize them. Huh? Okay, so now the only kind of little bit of math, numbers, very naive, simple. We're going to talk about relative versus absolute machining tolerances. And rather than looking at this, I hate slides with a lot of words. That's good for you when you're at home, you read through it. But I rather try to convey you the intuition, the concept. And so what I will do is I'll jump some slides ahead. And I go to this weird curve here. It's a strange curve, right? What I have here is relative tolerance versus the size of things. And what you see, it has like a peak, right? I'm going to try to explain where that comes from. And once you understand that, you'll kind of have a flavor of what I'm trying to convey to you. Relative tolerance. So if I build a house, and let's say I design it to be 10 meters long, this dimension, but instead of 10 meters, you know, it's like off by 1 centimeter or 2 centimeter. I have an error there, right? So to measure relative tolerance, you divide that error by the total dimension, by the size of the thing. That's relative tolerance. So now, for a long, long time, mechanical engineers called something precision engineering if the relative tolerance was about 10 to the minus 4. Now, this is kind of intriguing because in micromachining, nanotechnology, we can never achieve this. I'm going to try to explain this. I probably run a little bit too fast. I see already some of your eyes glazing over, especially yours. So, in micromachining, I want to make a line that's 100 microns long. And instead I end up with 99 microns. What's the relative tolerance? It's 99 or 101, so the relative tolerance is 1%, right? 1 over 100. So you know, my micromachining, even my nanotechnology, doesn't even qualify as precision engineering. Strange, right? Let's think about it some more. The objects that mankind can make with the best relative tolerance are about the size of a human hand. It's interesting, right? And to me that makes sense because, for example, I build a temple, a huge thing, the relative tolerance will be getting pretty poor. I will be somewhere here. Sorry, some 100 meters, let's say, temple, relative tolerance 1%, 10% or worse. If I make very small things, same thing. Relative tolerance is getting pretty bad. But those things that I can position very well, I can make a lens with relative tolerances that are amazing. 1 ppm, 10 to the minus 6, 10 to the minus 7. So I'm right here. So precision machining is 0.001. But there's technology now out there, like Fanuc makes robotic controlled CNC machines that works at a 1 nanometer level. We cannot do that with micromachining. It hurts your head, right? Because we always hear micromachining, nanotechnology, we can make such small things. Yes, we can make such small things, but these are absolute tolerances. In other words, I can make 1 micron, 100 micron, but I might be off 10%, 15%. Whereas with things that are the size of a human hand, I can make them with relative tolerances that are much, much better than either nanomachining or micromachining or building big things. Are you getting this? It's an important point. Who is not getting it yet? Not much sympathy here. So, trying it again. Why is it difficult to build huge things with an excellent relative tolerance? Maybe if I can solicit that answer, I feel if you understood it or not. How will you measure it? How will you control it, right? Right. So, sorry? Accessibility. How do you put this whole thing on an XY table? In a way, it all has to do with measuring it. How good can I measure and stay in control? Right? And so if things become very, very small or very large, you cannot position them very well. You don't have your human hands to control them. Right? And so, of course, this barrier is now more and more being broken. Why? Because we now have atomic force microscopes that allow us to build atom by atom. And so this whole paradigm might actually be shot through. And we might get into an era where we can build with atomic precision. And that's why nanotechnology and advanced manufacturing also coupled. There's a big link. It could be the next step for us to build things with absolute tolerance. That's atom is there or it's not there. That's pretty good relative tolerance, isn't it? So one more time, do we understand the difference between tolerance and relative tolerance? Can you word it? Can you kind of try to paraphrase it for your friends?
So whatever, it's on a large scale or on a small scale, it's really hard to control measurements, but as something that's like a regular size, and it's easier to control everything, so you get the tolerances a lot better.
Right, and now I'm going to tell you a secret why all of manufacturing is kind of connected. All the way from a lithography station to a CNC machine. What will they all have in common? They will have an XY table. And it's the control of that XY table that determines your relative tolerance. So how will you put the temple on an XY table? And then when you go so very small, how will you control the vibration that mess up your XY table? So there's a sweet spot in the middle that allows you to do the best job, and it's when you're talking about sizes of 10, 15 centimeters. And indeed lenses and a whole bunch of objects there you can make with exquisite tolerances at that level. So lithography, such as silicon micromachining, is excellent for small absolute tolerances. We understand that now. We can make it small enough. But for relative tolerances, ultrafine diamond milling is better. So if you have to decide about a machining technique, you might actually check what is your relative tolerance you require. And say, yeah, if you want that relative tolerance, don't make it that small. You better go to diamond milling, make it a bit larger, so that you can have that relative tolerance. That's what the second bullet point is saying. And so the third bullet point, in some cases, we might want to keep our micro machine somewhat larger to optimize relative tolerances, right? So that was really the only difficult concept we learned today, isn't it? All the rest, wasn't it? Like naive, simple, no? Philosophy, Stella, things like that. This curve, I will come back to tomorrow, is a very important curve. We will come to it many times. What it shows here is the date, and here it shows achievable machine accuracy. And look how we got better and better, making smaller and smaller items, either in normal machining, precision machining, or ultra-precision machining. I think picking that back up tomorrow will make a good link to the class of today. As we know, I only have 50 minutes today. And the last slide I will also come back to tomorrow. Because more people arrive towards the end of the class, I will summarize what I said in the beginning, so don't make any noise yet in parting moves. Parting moves. That's a strange word. So 165 and 265 are one and the same class. Unfortunately, there were some mistakes made. 265, the graduate didn't realize there is also this class on Mondays. So there is only one class. We're going to have a much bigger, more comfortable room. Tomorrow, the class is, where is it? It's in the Bren Hall, right? And that will be comfortable. That will be a big class. Okay? So altogether, I think there's about 58 students. We have 5 practica, and I told you what these practica are about. We will have to split you in groups probably about of 15 so that you all physically get to do something in these classes. And that's why we want to take advantage of these Mondays. Often that class will be about preparing you to do rapid prototyping, for example, or prepare you what is CNC machining all about. My ultimate goal is this. If you apply for a job and you said you know what a clean room is, or you know what rapid prototyping is, you know what CNC machining is, I think you'll actually score some very good points with many employers, right? Just even at that basic level, this should be very useful for all of you. It's not going to be your usual class. This is not a very difficult class. There's not too much math. It's a lot about concepts, right? And so for me, grading this class is often very difficult because you're often going to do group work, right? You're going to build, I cannot have everyone do CNC machining. So you're going to be taking pictures, put a PowerPoint presentation together about it, but you're going to do it in a group, right? So in that sense, what I praise a lot is your activity in class and be here, right? Because this kind of thing is hands-on, it's kind of hearing it, it's very difficult to get it from the web, right? Many people are now talking about classrooms moving to the web. Well, this kind of a class is one of those that's very hard to move to the web. Although it will be on the web, right? Isn't it? So thank you all.